Okay, hello everybody. In this video, we are going to talk about more polynomial functions and characteristics, and this time we are going to talk about even and odd functions. Now, I just want to preface it by saying, right now, this is the only time that you have really heard about even and odd, except for maybe signs, like positive and negative signs, but even odd functions we're talking about today. Do not get that confused once we start talking about even and odd degrees, because that will kind of be different situations and you really have to make sure that you understand what the context is. So even and odd functions, totally different than even and odd degrees when we're talking about polynomials. Okay, so we are going to start with talking about, before we get to even and odd, we're going to just talk about a little bit more information when it comes to tables. Now remember, we've already been able to identify characteristics of tables, meaning they can be linear, quadratic, or neither. We can tell if they are concave up or concave down. We can say a bunch of different things. We can also identify what degree, now that we know about polynomials a little bit more and that the degree means the x, the largest exponent, we can determine that information from a table of values also. The only little important part here, though, is that you do have to make sure that is when there are equal with input intervals. So if we take a look here, good thing with table A and table B is that is exactly what we have. Both of these tables already have those equal intervals, meaning in table A, we have intervals of 2, plus 2, plus 2, plus 2, and in B, we're plus 3, plus 3, plus 3, plus 3. So that criteria is already being met. Perfect. So then what we're going to do is we are going to be able to determine the degree of the polynomial by taking a look at the number of successive differences, the first differences, the second differences, the third differences, the 10th differences. Whenever those are equal, that's going to be the degree number. Okay, so let's see it in action. Let's take a look at table A. We know that we already have those equal with input intervals. Perfect. So now I'm going to take a look at how my output values are changing. So to go from -2 to -3, I have to subtract 1. To go from -3 to -1, I have to add 2. So already right there, I can tell you this is not going to be a degree of one polynomial because they're not equal. Then I have from -1 to 4 is plus 5, and from 4 to 12, that is plus 8. Okay, so definitely not first degree. Then we're going to go ahead and try our second differences. Here I notice that from -1 to 2, that's plus 3. From 2 to 5, that's also plus 3. And from 5 to 8, that is plus 3. So since we have our second differences being equal, we can therefore say this is going to be a degree of 2 because the second differences are equal. Now, if you don't want to say the degree is 2, because we should know based on what we talked about earlier in 1.4, this would make this a quadratic function. Okay, so that's what we can do. It could be the 10th differences. It could be whatever we want, but those successive differences are what we're going to look at to be able to see what degree the polynomial is. Go ahead and pause the video and try to give B a try and give B a shot. Once you think you've got it, press play. Okay, hopefully you were able to give this a try. So as I take a look at my first differences, those were not equal, so it is not a degree of 1. Then I looked at my second differences, still not equal, so not a degree of 2, so this is different than problem A. If I looked at the third differences, that did work out to be the same or constant, so therefore I would say this is degree 3, or you can say cubic. So either way, if you know the name of the function, you can say that, or you can just call it by the degree. Totally up to you. Now, one thing I do want to just mention is if this had not been the same, if this would have been a 2, and then all of a sudden I would have had to go to the next set of differences and say that that was plus 3, at that point, I can't say what degree it is. I don't have enough information from the function with those table of values to say that it is like the 10th degree or something like that. So here, I would have to say that this is at least It's not the first degree. I know it's not the second degree. I know it's not the third degree. So we would say it has to be at least a degree of 4 or higher. That's all we can do sometimes, so we can kind of narrow in that information, but we might not be able to, if there's not enough data, to say exactly what it is. Okay? Okay, then we are going to talk about even and odd functions. So even and odd functions. First thing I notice here when I look at this graph for an even function, I notice some symmetry. And you might not recall symmetry because I'm not sure you've seen symmetry since integrated 1 or integrated 2, but symmetry is like the rotational symmetry, the reflectional symmetry, translation, things like that. Those are those transformations that we talked about. And when I look at that even function, I notice that it is symmetric over the y-axis. Anytime you see that relationship, we can say then that it's going to be an even function. What this means, and before I show you the math part of it, kind of like the fancy notation of it, I'm going to show you an ordered pair. Basically, if I take a look at f of -2, evaluate what the function will be when x is -2, and I compare that to when x is 2, so the opposites, a -2 and a 2, a -3 and a 3, a -4 and a 4. If those two turn out to be the exact same output values, like I have here in these two ordered pairs, -2, -3, and 2, -3, then we can say that this function would be even. Now, the fancy way of saying that is that f of -x is the exact same thing as f of x. When I plug in opposite input values, I get the exact same thing out. I'm getting f of x or f of -x. They're both the same, so -3 and -3. Now, that's even functions. If it's not even, it can be odd. If it's an odd function, you would think it would make sense to be symmetrical over the x-axis. But for this example, it absolutely is not. Because if I look at that point around negative, well, even let's do -2 and 2, I do not have a point at -2, -2. So absolutely not symmetrical over the x-axis. However, if you're good at seeing this, and I'm not very good at seeing this, it does turn out to be symmetrical over the origin or around the origin. Meaning, go ahead right now, take your piece of paper, turn it upside down so that the name part is facing you or the title is facing you, and if you compare the two, they are the exact same. So that has rotational symmetry around the origin if you turned it 180 degrees, okay? If we take a look at a point, just like I did with the even function, if I take a look at this -2, 2, which I already did, and now I compare that to 2, you will notice that that is -2. So these are the exact opposite for output values. So how I remember this, okay, and use it or don't, it's totally up to you, but if I am talking about an odd function, it is symmetrical about the origin, and when I plug in those opposite input values, my output values are also opposites. So there's 4 O's in a row: odd, origin, outputs, opposite. That really does help me to distinguish the difference between even and odd. And then the fancy notation for this one would be that when I plug in that -x, I get the opposite of x. So we have that little extra component there, okay? So we have even functions. Inputs are always the opposite for input, even or odd, but the even, they're the same. We get -3 and -3. For odd, inputs are opposites always, but the outputs are opposites. That's what we're looking for. If neither of those things are happening, then it's a neither function. These are just two specific types, okay? So let's go ahead and through some examples. I'm gonna go ahead and skip the first couple, and we're gonna go to the graphs since we really focused on those graphs and the definitions. So press pause, try F out. Look at that one and decide if you think this is an even function, an odd function, or neither, and then be able to say why. When you think you've got it, press play. Okay, here we go. So when I'm looking at this, first thing I always do is I look for the symmetry. Well, y-axis, Absolutely not, because this point right here would have to match up with a point somewhere right there, and that does not work out for me. So it is not an even function. I can cross that out. With odd functions, like I said, if you're good at seeing that, for sure. And right now, what you might want to do, because I have the original on the screen, go ahead and turn your paper upside down. If you do that, or when you do that, it looks the exact same. It comes down right around when x is -2 through the graph, and it goes up right around when x is 2 through the graph, whether it is facing up or if it's facing down. So for that reason, it is absolutely going to be odd. But another way that I say this, and that would be my final answer, but another way I look at this is I pick those points. So when x was 1, I got a value of -3. That's right down here. When x is 1, y is -3. And then I'm going to compare that to the opposite input, and that's -1. And when I plugged that in, I got a value of 3. So because those are opposite output values, that's why I can say it's odd. So you can use either reason. You can say it's odd because it's symmetrical around the origin, or you can say it's odd because the output values are opposites. Or if you want to get fancy, you can also say because f of -x is the exact same thing as the opposite of f of x. Okay? Go ahead and pause the video again and try G. Again, if you're wrong, that's okay. Once you press play, you'll hopefully figure out where you made your mistakes and correct them. Okay? So go ahead, press pause, and give it a shot. Okay, back at it. I notice parabola here, and I think parabolas are symmetrical, especially over the y-axis. So I'm going to go ahead and draw my line here, and it turns out it doesn't match up. If I pay attention to those points, for example, if I look at -1 and 1, if this were an even function, because it's symmetrical over the y-axis, then I would have a point at 1, 1, and I don't. When the output values are the opposites, when the inputs are the opposite, the outputs are the same, and they're just not. So then I go ahead and I try looking at the odd function being symmetrical over the origin, and go ahead, turn your paper upside down. You will hopefully see that's not even close. The parabola would open down. So for that reason, we are going to say neither. It's not symmetrical over the origin or the y-axis. And when I plugged in those 1 values and -1, I got 2 random, totally different numbers, not a 3 and a -3 or a 3 and a 3, 2 totally numbers that have no relationship whatsoever to each other. So that's an example of a neither, okay? Now let's take that information and let's go ahead and apply that to tables. So here you will see in example 8, we have a table of values for h of x. So I could, if I wanted to, take the time and plot those 2, 4, 6, 8, 9 points, but I don't want to. I especially do not want to make a graph all the way to 19 and -19 for my output values. So instead, I'm going to do exactly what we did with the points. I'm going to look at those opposite input values. So when x is -3, I'm going to compare that to when x is 3. And right now, I notice that these two are opposites of each other. So right now, my gut is telling me odd because the output values were opposite. But let's keep going. Let's make sure that they are. I'm going to compare -2 and 2. Are those output values still opposites? And the answer is absolutely. 2 and -2. But let's keep going. Let's just make sure. Let's try -1 and 1. Are those two output values still opposites of each other? Absolutely. And last but not least, if I go to -4 and 4, those are also opposites of each other. 0 can't have an opposite because it's the same, and you'll notice that it's still 0. So this absolutely looks like it would be an odd function. Now the reasoning, we can't say it's symmetrical about the origin because we don't have any of that information. We don't see the graph. If you took the time to graph it, you could say that, but I don't. So instead, we're going to say one of two things. We can either say the output, I spelled that wrong, sorry. The output values are opposites for opposite input values. And those opposite input values will always be the same, whether it's even or odd. Or we could be real mathy about it, and we could say, because h of negative x is the exact same thing as the opposite of what h of x was. So you can use either one of those reasonings, okay? Okay, go ahead, pause the video, try B, and again, try. Look for some patterns. Don't just keep letting me talk. Press pause, give it a shot, look for what you notice, and then when you think you see something and you give it a try, press play and see if you're right or not. And if you're not, oh well, erase and make the correction. Okay, go ahead. Okay, so if we take a look here, again, I'm going to do the exact same process. I'm going to compare -3, oops, I want a highlighter, excuse me, -3 to 3. Ooh, they're the same. You notice that 8 and 8 are the exact same. I'm going to compare -2 and 2. Those also are the exact same. Let's keep going. Let's try -1 and 1. They are also the same. And let's just try one last one. Let's try -4 and 4. All the same, perfect output values, and 0 can't have the opposite input value. So I would definitely say that this is an even function. And I usually just stick with the math because I know that p of -x is going to be equal to p of x. If you don't know that or you don't like writing it that way, then you would just write it exactly like we wrote it up here. But instead, and actually let me just go ahead, I'll just copy this. And instead of writing it this way, we would say that the output values are the same. For opposite input values. That's the only thing that would change. I would change our opposite to are the same. Okay? Okay, so that's graphs and tables. Now let's take a look at equations because those get a little trickier because we have to do some simplifying. So first thing I have is m of x. Well, both of the definitions compare m of x to m of -x. So that's the first thing I'm going to do. I am going to find m of -x. Now remember, when we are evaluating, oh, my pen just died. So bear with me. Let's see if I can forget this device. 1 second. Sorry guys, my pen died, and if I have this connected, I can't use my finger. So hopefully that will work. Okay, so now let's try. So if still doesn't work. Just give me a second. Sorry guys for the hold up. I always have a problem with disconnecting this. Okay, so just bear with me here. Hold on, I'm gonna unplug my screen for a second and I'll come right back.